this is the second lecture on continuous system, where we will be still talking on axial vibration in bar, and we will look into how to find out the natural frequencies and mode shape of a bar or a rod, if you want to call it so, for axial vibration. So, in the last lecture we had talked about finding out the equation of motion or the governing equation for a bar under longitudinal vibration. We have seen that for longitudinal vibration we have this equation which was del by del x which was del by del x into E A x del u by del x, and that was equal to m x into del 2 u by del t square. So, this equation was derived in the last lecture. So, where we have talked that u x t is the longitudinal or axial displacement, and which is the unknown and which need to be figured out. So, we have seen that also that under normal mode of vibration, u x t could be written as phi x and t t, and then once it was substituted into the equation of motion, we got this as d d x by into E A x into d phi by dx is equal to minus omega square into mx into phi x. Then we had solved this equation and we have seen that phi x, the solution of phi x is c into sin beta x plus c2 into cos beta x, considering, so this was only for considering uniform cross section, considering that the area Young's modulus and the mass per unit length is not changing with x. We have seen for this particular case the solution of phi x is of this form, where beta square was nothing but omega square m by E A. This we have derived in the last lecture. So, now our job is to find out phi x in totality. So, in this expression for phi x, which is the mode shape, I do not know C1, I do not know C2 as well as I do not know B. So, therefore, my job is to now find these three conditions. So, how are we going to find this? This is going to entirely depend on the boundary condition of the bar that we are dealing with. The boundary conditions of the bar can be several. It could be a fixed boundary condition, it could be a free boundary condition, it could have a tip a concentrated mass at one of the end, it could also have a spring at one of the end. So, there could be n number of possibilities of boundary condition. Let us deal with the first case, which is a fixed free bar, that is one end of the bar is fixed, that the displacement at this end is 0, while the other end is free with no externally applied force acting at that point. So, now if this is the condition, then let us write down what are the boundary conditions for a fixed free bar. So, if we write down the boundary conditions, so this is x equal to 0, this is x equal to L. So, the boundary condition states that at x equals to 0, the displacement is 0. So, u 0 t is 0. For any time instance t, u 0 t is equal to 0. So, under normal mode of vibration, under normal mode, this can actually be written as phi 0 into T t is equal to 0. So, under this special condition of normal mode of vibration. Now, T t cannot be equal to 0 for all time instance t. That is a very trivial case. So, we say that T t cannot be equal to 0 for all t, for any arbitrary t. So, therefore, my phi 0 has to be 0 to satisfy this boundary condition under normal mode of vibration. If that is the case, then I have one boundary condition as phi equals to 0 at x equal to 0. If I impose this boundary condition, then I get C2 is equal to 0, because at x equal to 0, phi x is C1 sin beta 0, which is 0, and C2 cos beta 0. Cos beta 0 is 0, and so C2 is what is left with, and that is equal to 0. So, I get C2 equals to 0 from the first boundary condition. Therefore, my mode shape now is going to be C1 into sin beta x. Now, let us look into the second boundary condition. The second boundary condition at x equal to L is that there is no force at x equal to L. So, F L t is equal to 0. So, that can actually be written as E A del u by del x. F x is the internal force, and since there is no external force, since we are considering a free vibration case, since there is no externally applied force at x equal to 0, the internal force F x t is also equals to 0. So, which in turn can be written in terms of the displacement as E a del u by del x at x equal to L, and that is equal to 0. So, this can in turn be written as phi dash L into T t is equal to 0 under normal mode of vibration. Therefore, T t again cannot be equal to 0 for all time instance t. So, I am left with phi dash L is equal to 0. So, I know phi L is C1 sin beta x, and therefore, phi dash x is beta into L into C1 into cos beta x. Therefore, phi dash L Now, let us try to solve this equation. So, this equation has three possible solutions, that beta is equal to 0, C1 is equal to 0, and cos beta L is equal to 0. But beta and C1 cannot be equal to 0. If they are equal to 0, then if C1 is equal to 0, my phi x is always 0. So, it is a trivial solution. Again, if my beta is equal to 0, then also phi x is equal to 0 is, which is also a trivial solution. So, beta and C1 cannot be equal to 0 for non-trivial solution. Otherwise, the solution is going to be trivial. So, for non-trivial solution, my beta and C1 cannot be equal to 0. Therefore, the only option left is cos beta L is equal to 0. Now, we have to see what makes cos beta L equals to 0. So, cos beta L is equal to 0 can happen when beta L is equal to 2r minus 1 pi by 2, where r is 1, any integer value n, all possible integer value. It can go to infinite value of an integer value. So, when beta L is odd multiple of pi by 2, then cos beta L is going to be 0, or beta is going to be 2r minus 1 pi by 2, where r is all possible integer values. Now, if this is the value of beta, we have seen that beta square is omega square m by E A. That is what beta is. So, this is going to give us omega as 2r minus 1 pi by 2l root over E A by m. I will put a subscript r because the expression on the right hand side depends on the integer value of r. So, this is the expression for natural frequency. So, this is the expression for natural frequencies of a where r is equal to 1. Okay. So, therefore, we can see from mathematical derivation also that there could be infinite possibilities of natural frequency that exist for a continuous system. For each integer value of r, I am going to get a natural frequency of the system. So, once we have found out natural frequency omega r, we now know the value of beta r. So, let us try to find out the expression for mode shape. So, if we try to find out the expression for mode shape, I have said that phi x is C1 sin beta x. Sin beta is nothing but 2r minus 1 pi. Okay. So, why to keep r? So, let me just erase this 1 and replace it by r. So, this is also a function of r. So, therefore, this is the mode shape of a fixed free bar. Okay. R is again 1, 2, 3, n. So, this is the rth mode shape. So, instead of just calling it mode shape, I can also call it as the rth mode shape of a fixed free bar, and we can also see there are infinite possible solution of this mode shape. So, again to repeat, a continuous system can have infinite number of natural frequencies and mode shapes. Now, we have seen for a multi-degree of freedom system that the mode shapes which was in forms of R for a multi-degree of freedom system were orthogonal to each other. Okay. So, we have seen RP, RQ were orthogonal to each other. Now, let us look into what is the orthogonality condition for a continuous system. So, if we look into orthogonality, So, orthogonality for a continuous system can be written in this form. So, the same thing that existed for a multi-degree of freedom system. For a multi-degree of freedom system, it was a product, matrix product, or a product of the modal matrix into the mass matrix into the modal matrix or modal vector was 0 when the two mode shape of two different normal modes were considered. The same thing, the same condition exists for a continuous system as well. The only difference is that since here the mode shapes are a continuous function of the spatial dimension, that is x, we have to find out the integral of the mode shape with respect to the mass matrix, and that integral is equal to 0. Therefore, the integration between 0 to L, where the L is the length of the bar or any other one dimensional continuous structure that you can think of, in which into integral, and within the integration we have the mode shape of one normal mode into the mass distribution mx into the mode shape of the other normal mode, and this integral is equal to 0. Now, for our particular case where we have a uniform cross section, this expression can actually be written as CR sin beta r x. Our mass was constant m into Cs into sin beta s x dx is equal to 0. So, that can even be written as 0 to L m C r C s sin 2 r minus 1 So, one can always evaluate this integral and see that this integral is going to become 0, saying that phi r x is orthogonal to phi s x, right. So, now we will prove that why the mode shapes are going to be orthogonal, and the orthogonality will be of this given form in sometime soon, but right now let us just write down and understand the expression for orthogonality for a continuous system. Now, once we have talked about the orthogonality, let us now find out the mass normalized mode shape of a continuous system. The mass normalized mode shape of a continuous system can be found out in exactly similar way as we did for a multi-degree of freedom system. So, to find out mass normalized mode shape, what we do is that we take the integral between 0 to L and then we say phi r x into mx into phi r x into dx, we forcefully equate it to 0. So, in our case this is going to be 0 to L C r square sin square beta r x into m, since the mass distribution is constant, that is equal to 0. So, this we are going to forcefully make it equal to 0. So, that is going to give us the value of C r square or C r. So, if we evaluate this integral, sorry, I am sorry for this mistake. we are going to make it as 1, sorry. So if we forcefully make it as 1, then we will see that CR is going to come out as 2 by ml. Therefore, phi Rx is going to be 2 by ml sine so this is the mass normalized right. So, we see that this is the mass normalized mode shape of a fixed free bar. So, we will see later that similar to multi-degree of freedom system, making a mass mode shape mass normalized is going to ease the calculation when we do modal analysis for a continuous system. Now, let me move into a next example where we have fixed bar. Okay. So, let me get into the next example where we have a fixed bar. So, unlike the previous example, here both the end x equal to 0 and x equal to L is fixed and we will try to find out the natural frequencies and mode shape of this bar with the given boundary condition. So, we have to proceed exactly the similar way. We know that the generic solution for the mode shape is C1 sin beta x plus C2 cos beta x. Now, let us look into the boundary conditions of the bar. If we look into the boundary condition at x equal to 0, u of 0 t is going to be 0 because displacement is constrained when we have a fixed end. So, under normal mode of vibration, this can be written as phi 0 into T t is equal to 0. Therefore, from this again by using the similar logic, this cannot be equal to 0. So, phi 0 has to be equal to 0. So, this is going to make C 2 equals to 0 and therefore, my phi x is going to be C1 sin beta x by imposing the first boundary condition. So, what we are going to do next is we are going to impose the second boundary condition, that at x equal to L we have again u of L comma t is equal to 0, which gives us phi L is equal to 0. Now, I have phi x as C1 sin beta x. Therefore, I can say C1 sin beta L is equal to 0. Now, let us see what is the solution of this expression. So, C1 is not equal to 0 because if C1 is equal to 0, then phi x is going to have a trivial solution. So, C1 cannot be equal to 0 for non-trivial solution. Non-trivial solution. Therefore, the only other option left is sin beta L is equal to 0. So, in order to make sin beta L equals to 0, beta L has to be integer multiple of pi. So, r should be integer multiple of pi, where r is equal to 1, 2, 3 till n. R cannot be equal to 0, because if r is equal to 0, we are again going to have a trivial solution of phi x, which is not possible. So, therefore, beta is equal to pi r by L. Now, if beta is equal to pi r by L, then we can say that omega is equal to pi r by L into root over. So, I will put a subscript r. So, this is therefore the rth natural frequency of right. So, this is one part of the problem solved. So, now let us find out the second part, that is the mode shape of the system. So, we have therefore know that phi x is going to be c into sin pi r x by L. So, let me put the subscript r. So, therefore, this is the rth So, this is the rth mode shape Now, if we try to mass normalize it, how are we going to mass normalize? We are going to follow exactly the same procedure that we have done. So, mass normalized So, this integral has to be forced to 1. So, this integral is going to become 1 if C r is root over 2 by m L. Therefore, my mass normalized mode shape is root over 2 by m L into sine. So, this is the mass normalized So, with this we will end this lecture. So, in this lecture we have found out how to find out the natural frequency and mode shape of a bar under various boundary conditions. We have talked about what is the orthogonality condition of the mode shape of a bar, and we have also talked about how to find out the mass normalized mode shape of a given bar with a certain boundary condition. Thank you.